Cool. All right. So yeah, thanks. It's great meeting you all and everything like that. I'm going to try to go right into it because I realize this is a big section. You guys are being introduced to, well, you've done supervised learning, whether you know it or not. But this is going to be your first classification of supervised learning. So that's pretty cool. So thanks again, like things are a little wonky, to be honest. Like I kind of learned about an hour ago. It's like, hey, can you do a study group? And I'm like, sure, why not? So just kind of bear with me, right? But real quick, just give me a quick thumbs up, who's like, it's section, I think mod 3, section 25, right? Just give me a quick thumbs up if you guys kind of breeze through it, you're feeling pretty good, understand the material. Give me a sideways, you're like, I kind of looked at it, but I really haven't practiced it, or I don't quite understand it. And down, like, it's like, I don't even know anything about logistic regression. Give me a thumbs up, sideways, down. Mostly sides. Okay, cool. That's good. I like the sideways because that means there's room for this, right? And usually I like to say is that people who give me sideways like this, sometimes it really means closer to down and they're just being polite, stuff like that. And that's perfectly fine too. All right, so let me go ahead and share my screen and we'll go through. And I see Alex seems easier. Okay, easier than maybe the other stuff. So while I'm kind of pulling up my screen here, just give me a thumbs up. You guys have learned linear regression. How do you guys feel about linear regression? Thumbs up, thumbs down, sideways. Cool. You guys did a project on it, right? So hopefully you're feeling pretty good. All right, so let me share my screen. So, oops, are we not sharing? All right, cool. And of course, Zoom. I don't think Zoom likes me this morning, or it's still morning for me. I'm Pacific Coast, so. All right. All my windows got moved around. Okay, so we're going to dive right into logistic regression. So I'm going to give you a secret. Logistic regression is really just linear regression, but on the logistics. Interesting, right? So we'll kind of go right into this. If you read through the material, or through the curriculum, you'll kind of see some of the stuff. I might rephrase it or kind of present it in different ways, but hopefully this kind of gives you another frame. And if you haven't read the material yet, this is good because it's kind of like a good introduction, and then you can go into detail, especially playing around with the labs and everything. Okay, so logistic regression from linear regression. So how is it used? So first thing we need to talk about is linear regression. So linear regression is really about trying to find a relationship, right? Whether it's, I don't even know what we call it, simple linear regression, right? If you have like one variable, like one feature and one target, basically you're trying to find a relationship between those two, right? So think of like, like a 2D plot. And if you remember, and I'm just gonna kind of draw this just to put a picture in your head, is we would have something like a variable, we'll call that X, we'll call our target Y, right? And then we have some data points, some great data points that I can't draw great dots on. And then you're like, cool, like those are my data points. And you basically want to find the best line that predicts all of those things through, right? All right, this basic stuff, right? Of course, if we have multiple variables, if we have X1, X2, X3, X through 100 or whatever, how many variables you have, remember they can be categorical, they can be numerical, right, continuous. And basically we have this multiple parts and we're making an equivalent of a linear line through all those data points. So for 3D, that would be equivalent to a 2D plane, right? And of course, we can always look at a snapshot. I always think of it like, if you imagine three-dimensional, I'm not going to draw this really well. So, but if you imagine like 3D, like on the X, Y, Z platform, usually I'll call it X1, X2, and then Y being your target. You have some kind of like papery kind of thing going through all the points. And if you imagine, if you kind of like tilt it so it's like in the right direction, it'll look like your plane is like a line. And that's really like how we can think of like, oh, linear regression really is just a bunch of little simple linear regressions put together to make a multiple linear regression. Okay, so that's the way I kind of do it. For just like saying multi-dimensional space, and hyperplanes and stuff like that. I think sometimes that can be just fanciness to be just confusing. So anyway, have this picture of linear regression. It's really about finding relationships. So with classification though, okay, so with linear regression, we're saying, okay, we put these inputs in, X1, X2, X3, X through 10, whatever, right? We could put these values in there and then make a prediction based on this red line. And that red line really is the prediction of like what we think the target value will be. And the Y value, the target, is continuous, right? It can be, for example, I think you guys did housing prices for the project last, right? Yeah, so you can think of your housing prices could technically go from like, 0 and above, right? I mean, I think maybe you guys have maybe played around with this. If you got a really bad prediction, you could actually predict it to be less than 0, right? Which means like if you were to buy the house, it's not even worth you buying. Essentially, you have to pay money to buy this house. Of course, how realistic is that? Who knows, right? But there's a prediction, right? So it's some continuum, right? From negative infinity to positive infinity. Well, classification, which we're going to talk about now, and one of the methods we're going to do is logistic regression, because it's basically linear regression, is instead of saying, you know, okay, what is this, you know, continuum value? We're really just going to be looking for, is it this or is it not this? Yes or no, which sounds, you know, pretty simple, right? Basically, you're saying, hey, is it the target is yes or no, right? So I like to say, like, you're with us or against us, right? So that's really what logistic regression does, which sounds like, hey, this sounds pretty simple, right? But we're going to find is that how exactly do you talk about that from maybe continuous variables? So we'll kind of give some examples of that and everything. All right. I might just kind of fly through linear regression. This is what I usually would have for my cohorts and stuff like that, what I had already planned out something differently. So I'm kind of playing it by ear. Okay, so if you went through my cohort, you might have seen, you would see this equation before. Does this equation look familiar to people? I think the curriculum has something similar to this. Awesome, cool. So just know y hat is our predicted value, right? It's our predicted target value. And then we have beta 0, beta 1. These are just constants, right? So these are just some numbers that we find in here. And this actually is the full length of our linear regression. And you can see here is I have this nice little summation of math. Ooh, beautiful math. I love math, right? And you can see this like all summarized. Basically, that is linear regression. So really easy, really nice and cool. Okay. So we're going to see something similar with classification and logistic regression. I'm going to warn you right now is that there is math. It's also not exactly what we do with logistic regression, but it'll hopefully be familiar enough to kind of see where this relationship comes from. Okay. So right here, we have our linear regression and we have our logistic regression. Now, this is a picture I pulled off of the internet just really quickly, but you can kind of see like, oh yeah, linear regression, we have some kind of like line, right? Logistic regression, we're gonna have what we call like a logistic, or we can also sometimes call this a sigmoid function. Basically, it's got this nice little S-curve kind of thing. Note that also it can technically be flipped over, right? So it can be pointing the other direction, but in general, we have it, we form the target value. So we have this nice S-curve like you see on this picture right here, okay? And so what we're gonna do is we're gonna try to essentially, instead of trying to fit the points on this straight line, we're actually gonna try to fit the points on this logistic. And this logistic curve, right, the sigmoid curve, is going to basically tell us the probability of a single point based on its value of, is it gonna be in class 1, like yes, or is it gonna be class 0, meaning no? And so you can see here, these red points right here, and this is, again, this is just something I pulled off the internet. They really should just be all in a straight line here. I think someone just manually put points on here. But it would be a straight line here because you know, right, on your data, supervised data, you already have the target. We know some examples already. You know, basically it's either 1 or it's 0. So you're gonna have this x-axis here, which is a feature, right? So the one I have example of this is like, imagine you have people in, I'm just going to use weight, right? So weight can be a spectrum, right? It's like we have different weight and stuff like this, and we want to predict, will they have heart disease or not, right? Now, obviously, as you probably can kind of think about this, is that if you have a child, right, like there's a very unlikely that they'll have heart disease, they'll be smaller weight, but you also have maybe adults who are lighter weight, you know, who don't have heart disease, but you can also have someone who's very, you know, underweight, right? They don't weigh very much, but they can still have heart disease. So it's not going to be perfect, right? But we can get an idea of like, you know, like, okay, in general, if you tend to be heavier, you tend to have heart disease, but not everyone who is heavier has heart disease. Does that make sense? Yeah. So in that case, what that graph would look like, it wouldn't look exactly like this. What it would look like, more likely, I'm just going to draw, is if we have our graph like this. And I'm going to use blue. Okay. So you can think of 0 down here. 0 meaning false, right? This person does not have heart disease. So this is going to be a little confusing, but like a happy heart, right? Okay. And then we have heart disease up here, which is 1 on the y-axis. And we're just going to put like an X through it. Bad hearts. Okay. No offense to anyone who has heart disease or anything like that, but you know, it's like, oh, okay, something's wrong with their heart. So we have our weight down here, which is our x-axis, right? And we can imagine like, okay, there's some people who are lower weight, like think children or, you know, relatively healthy people who are, you know, been keeping up, you know, they exercise all the time, eat well. So they're less likely to have heart disease. And we'll tend to see, you know, most points down here, right? And then as people are kind of heavier and stuff, not everyone who's heavier has heart disease. So we definitely would have some points in this part. And note that this should technically be on the x-axis. I'm just moving it up so it's easier to see. So these are all the ones that are 0, right? And then we have people who do have heart disease. So we might tend to see, I'm just gonna put a few extra points, because there tend to be more people who are underweight, like not as heavier, right, that don't have heart disease versus probably heart disease. I'm just making up a number, but I think that sounds about right. And then we have some people who are heavier, right, who have heart disease. But we also have some people who are lighter who also have heart disease, right? And so our goal basically is to try to fit, and I'm just going to use green here. That should be fine. And I'm going to try to fit a logistic curve that's going to say, okay, this is going to represent the probability. So if you are on here, this goes from 0 to 1, right? So what that means here is that if I follow up this line, right, and think of what the y value is, basically it's like, oh, the probability, the y value here is very, very small. And then we start going up and up and up and like, okay, the probability is getting higher and higher and higher and higher until we approach 1. Now, this logistic curve, you should know, is that it's asymptotic. It'll never reach 1, right? It gets closer and closer and closer, which also makes sense, right? Someone could technically be, 5 million pounds, 5 million kilograms, right? But you never know for sure if they have heart disease. Of course, that person probably doesn't exist. But the point is that you can say, okay, like we never know for sure. There's a possibility they don't have heart disease still. And that's what that logistic curve is really trying to represent. And so you can imagine if we're right here, for example, and let's say this weight is, I'm just making up some scale here. Let's say this is 50 pounds. Let's say 50 kilograms. That seems a better number. 100 kilograms, right? Maybe it's like 150 kilograms. So for about like 100 kilograms, right? You're like, well, like that's like about, let's just give like, that's about like 0.2. So that means if you're 100 kilograms, at least based on this, logistic curve, right? There's a 20% chance that you have heart disease, right? But if you're closer to maybe like, let's say 125 kilograms right here, you might have something closer to like 80% chance, right? 0.8% chance of having heart disease, okay? And that's really what logistic curves are doing for us. And this is what logistic regression is going to do, is that basically we then say, okay, and we'll go into more detail about this in a second, but I'm going to use, well, why not, magenta, is that basically, okay, like if anyone is past 50%, let's say that's the 50% mark right here, that means anyone who is past this 50% mark, if you're more than 50% likely to have heart disease, then we're going to say you have heart disease. Okay, that's how we're going to make a prediction, right? Because it's either yes or no. So when we do that, it's like, okay, this is like 50%. Then we say, okay, well, where would that be on the weight, right? It's like, oh, well, on weight, that's like something like 110 kilograms. So basically we make this thing, it's like, okay, this threshold right here, if you're under 110 kilograms, we predict based on a logistic curve, based on our model, we call it, we predict that you don't have heart disease. If you're over 110 kilograms, right, then we predict that you do have heart disease. Now you might say, oh, that might not be quite right? Maybe 50% chance is too high, right? Like that's too high, not too high of a threshold, it's too low of a threshold. Like we can see there's still a lot of people who don't have heart disease. So maybe, for example, you say, okay, well, if you're at 80%, right? If we see you have an 80% chance of having heart disease, then that's what we'll say, okay, that's when we'll classify you as having heart disease or predict that you're having heart disease. And you can see if I do this guy right here, that's maybe closer to like 130-ish, right? So this is kind of the idea of logistic regression. So once we have this curve and we know this curve fits really well, how do we figure that out? We can actually make some predictions, right? And get an idea. Now we'll still get some things wrong. For example, this person who is very, very light compared to everyone, on the average, they still have heart disease, right? So we'll obviously not predict them really well, but we can do this for multiple variables, multiple features, right? Just like we would do for multiple features for linear regression. Does that make sense? Okay. And the way I kind of picture this around here is you can kind of think of like these multiple like different values, these different features. You can think of them like, when we see this little graph of a 2D graph, they're like almost slices. I will note is that the way logistic regression works is with linear regression, you can separate each variable out really quickly, right? I say, oh, this is like how much is contributing to the overall prediction, like the regression, right, of this much of the target. With logistic regression, you really can't do that. They're kind of very closely tied together. So you won't be able to directly make this like slice and have a logistic curve. So there's not like a direct slice you can have and look at this, but it kind of helps to kind of think, oh, you can have multiple features in this and they would combine together to make a prediction of, oh, at this threshold, we would say you have, heart disease or not have heart disease. Okay. Does that make sense to people? Give me a thumbs up, looking good, sideways. Any questions?
Yeah, a quick question about what you just mentioned. I guess compared to normal linear regression, then it sounds like that kind of eliminates multicollinearity between different variables or features.
Yeah, so it does add some extra complexity, and this is where you guys learn about polynomial regression, right?
A little
Like
bit.
a little bit, right? So one thing is you can have interacting features, right? Linear regression or logistic regression is going to basically inherently use like interacting features. Like that's not technically the right term, but that's kind of close to it, is that we're going to combine together. And I'm going to show you guys in a second when I scroll down here. If you remember, this is our linear regression line right here. We're going to transform this into what logistic regression is going to use. And you'll see immediately from the equation, you're like, oh yeah, there's not an easy way for us to separate it out. But yeah, does that kind of clarify things, John?
Yeah. Keep going,
Okay,
please.
cool. All right, any other questions about this? Because I'm going to clear it out and then remove it. Cool. All right, so let me go ahead and clear that guy out so I can scroll down. So kind of going off of what John was saying, right? So like, okay, like, you know, how you separate these things out, you really can't, right? So this is kind of, note this is not technically the right equation for logistic regression, but it kind of gives you an idea of like what's going on here. Is essentially we're going to take this linear regression and basically convert this over to logistic regression. And essentially what's going to happen here is that we have our target, our predicted value from our linear regression. It's going to be part of this exponential. And you can see here this exponential now, if we expand this out and kind of simplify this mathematically, right, we actually get these interacting features. So now we have, you know, x1 all the way x2, x3, x4, all through xn right here. They're being multiplied together with the power, right? So that means they're not easily linearly separable, which, you know, for logistic regression, it's just kind of like what that's kind of like the, I don't know if the trade-off is the right word for it, but it's kind of a little bit of a trade-off. There are statistical tests that you can do to say, hey, let me do a statistical test on this variable, right, and see how well it works. So for example, if we had like heart disease and we had like things like weight, height, you know, let's say, do you eat vegetables, you know, 3 times a day or something like that. And then we had something like what color your car is. The thing is, your color of your car is going to have an effect in this logistic regression. Whether or not it's a meaningful like feature is a different kind of story. And it's not going to be as simple as like, oh, you just separate this out and see how much an effect it has, like you would have with like you guys, when you did, you guys probably use stats models, right, for linear regression. So you can see like the p-value, for example. It's not going to be as simple as that. That p-value is going to be a different kind of test. So you can test individual parts, but it's going to say, is it statistically significant enough? So it's not going to be directly built into how the formula works for logistic regression, but it is possible. Okay. So big thing about logistic, like hopefully this all makes sense, is that we are basically trying to find this logistic curve, this sigmoid function, right, that best is going to, you know, quote unquote, best predict, you know, whether someone does have heart disease or not, right, or whatever the classification we do. And so one thing I'll kind of note is that basically we take the log of odds, which is represented like log of the probability, so p divided by 1 minus p, and we're using maximum least likelihood, or like maximum least likelihood estimation. You guys remember that, like back in Mod 2? Everyone loves MLE, right? If you remember that great big math of junk and stuff like from the curriculum. Main thing you have to know is basically we just keep making different linear logistic curves until we basically get a good fit of like what we would expect. And so MLE, if you like, give me a thumbs up. How do you guys feel about MLE? Like you're like, yes, I understand this completely. And thumbs down, like I still have no clue what this math is supposed to do. To like, maybe. Okay, I see some thumbs down, I see some sideways, yeah. And thumbs down, I will tell you the biggest thing you have to know for MLE. Basically, it's saying, hey, let's ignore what the actual, like what we think this prediction is gonna be. And say, what if we pretended that we had this certain distribution for each individual point? And then we say, okay, what's the most likely distribution they have? So this is a little bit of tangent, but I think it's kind of important just to know like what this is, because I think it's gonna be kind of confusing. If we have this curve right here, let's say this this is different values, right? And let's say this is like weight. And we have like a distribution. So this is like one univariate. Okay, and we have a bunch of data points. Hopefully you guys can see that okay. And then we have some points right here. Basically, our thing for MLE is like, what if we had a curve? I'm gonna use a different color. Let's try this light blue. So we have a curve like this, or a curve like this. Like this is like normal distributions, but I'm really bad at drawing. And we have a normal distribution like this. Of these distributions, A, B, C, just based on this data, so you can see these data points, very poorly drawn, but you can see them here, is which one of these distributions would most likely fit these data points, A, B, or C. And remember, the distribution is like how much probability, right? Most of them land right here, most of them land here, or most of them land here.
Should be B.
I'm sorry, say that one more time.
B as in boy.
B as in boy, yeah. Give me a thumbs up if you guys agree with that. Awesome, you guys did MLE. That's what MLE basically is doing. It's saying, hey, based on the data, what's the most likely like distribution, most likely curve that's going to represent this? And that's what you're basically doing. We can talk about exactly how you calculate this, but that's essentially what MLE is really trying to say. Okay, so just kind of know that's the general idea. You can definitely go into more like about what specifically how it's calculated, but my focus right now is just to get the idea of like how we determine this. Essentially, it's from the data points themselves to determine the distribution or the curve. Okay, and that's what we're doing with logistic regression. All right, cool. Sound good enough? Understandable, at least theory, right? Okay, and I didn't go into full math details because we can always go deeper into math later on, right? But we're data scientists. We want to do things too, right? We actually want to try things out. So let's try to implement this in actual notebook.